Recording.
Okay, so let's start our session of this week. We have a pleasure to have with us today. The first talk is from Fabricio Macia from University Polytechnic of Madrid. So thank you very much for accepting the invitation. It's also a pleasure to me to congratulate you of your recent success in the selection process and your recent position of catedrático of Universidad. Congratulations.
Thank you.
So Fabricio is a specialist in control of PDEs and spectral theory. He did his PhD thesis in Universidad Complutense de Madrid. And after that, he was a postdoc at Pizza University and the École Normale Supérieure. He has a Juan de la Cierva Research Fellow, and since 2008, he has a joint University of Polytechnica of Madrid. Among his research, I would like highlight his significant contributions to control theory, working with Nalini and Taraman on the controllability of Schrödinger equations on the torus and disk. So today he will give a talk on control of magnetic Schrödinger flows. So thank you very much, and you can start.
Thank you, Anna, for the nice introduction, and thanks to all the organizers for the invitation. Very happy to give this talk. So today I wanted to talk about joint work with my collaborator and friend Gabriel Rivière from Nantes. So together with Gabriel, we worked a little bit on questions related to control. And last 2 years ago, I was visiting Gabriel and started to work in magnetic fields, and more or less we found out that there were nice applications of ideas we already used for non-magnetic settings to the control of magnetic Schrödinger equations. So I want to tell you what we've been doing. So my starting point is, now we start from the beginning, so explaining a little bit the geometric setting. So magnetic fields and magnetic Schrödinger equations are not so easy to describe. So I will start from scratch. I will start with what is the basics of electromagnetics. So the starting point is the Lorentz force. If you have a particle that is moving in R3 under the action of a magnetic field, then this particle is the motion of the particle is described by the Lorentz force. So the Lorentz force is simply the vector product of velocity times magnetic field. The magnetic field has to be divergence free. Okay. So the equations of motions are simply Newton's law. So you have that acceleration is equal to the force. So I'm taking mass equal to 1, charge equal to 1 here. And these are the equations of motion, okay? So if you want to do the quantum version of this, it is better to write the equations of motion in Hamiltonian form. So this is something that you can do. And so since we are in R3 and B has divergence equal to 0, you know that there exists a vector field A such that the curl of A is B. Okay? And once you have everything written in that way, you can write the equations in Hamiltonian form. Hamiltonian form means that you can describe velocity and variation of momentum in terms of a single function, the Hamiltonian, which describes the total energy of the system. And this total energy of the system is simply this. It's the difference between the momentum P and this is called the vector magnetic potential. Okay, so the distance between the square distance is the energy of the system. So in this talk, I will be interested in understanding what happens when the motion is confined to a surface. So the easiest case is when the surface is a plane. So if our surface is a plane x3 equal to some constant, then the magnetic field is orthogonal to these planes, and it's described by a single vector field acting on R2, okay, by this thing. So if you have a function of this type and you take the curl, then you get something of this form. Okay. So the quantum version of this, if we are in Euclidean space, is not so difficult to get. So quantization, so you get a Schrödinger equation from this classical Hamiltonian by the process of quantization, which means that we replace uh, position by multiplication by x and momentum by essentially partial differentiation with respect to x. If I formally do this substitution into the Hamiltonian, I get the following equation for the wave function, which is the object that describes the dynamics of a quantum particle. Okay, so the wave function satisfies this equation here. So you see here is simply the Hamiltonian I had in the previous slide, where I've replaced the momentum by dx and kept x the same. Okay, so this is a PDE of order 2. And the physical meaning of this PDE of order 2 is simply that, if, for instance, using this function, you can compute any quantity that is relevant to the dynamics of the particle. For instance, if you want to compute the position, so the wave function, when you take its modulus square, gives you a probability density. And if I integrate this density on some open set, what I get is the probability of the particle being at time t in some region u. Okay? I'm ignoring all constants here because this p correspondence between p and dx, I should have added maybe some Planck constant, but I'm ignoring physical constants. By rescaling, you can reduce all the dynamical aspects to this very simple equation. Okay, but this is not what I'm going to do. What I'm going to do is to try to understand what happens if instead of a plane, I have a closed surface. Okay, for instance, a sphere, a torus, something like that. Okay, so if the motion is constrained to a surface, what is the analog of magnetic fields and so on? So there is some geometry here, it's not completely trivial. So the magnetic field now is no, you see, in a previous example, we had that the magnetic field pointed in the outward normal direction to the surface. So if I want to give an intrinsic description of the magnetic field, I can no longer use a vector field on the surface because vector fields are tangent. The correct object to look at is a two-form, okay? If you don't know what it is, it's not important. Essentially, since we are in dimension 2, two forms are described simply by a scalar function, okay? And well, if I take one of these two forms, because I am in dimension 2, automatically I get that the exterior differential is equal to 0. Okay? This is because I'm in dimension 2. So this is the equation that is analogous to the divergence equal to 0. Okay, and of course here the topology can be more complicated. So a surface is no longer simply connected, it's no longer like the plane. So in general, one is not always possible to find. So the question we had in the previous slide was that B was equal to the curl of something. So this is no longer possible here. Okay, it depends on the topology and on B. In any case, one can always write, in spite of this not being true, this B equal to dA alpha not being true, you can always write the dynamics as a Hamiltonian dynamical system. Okay, so I will try to keep things simple and stay in a setting that is very close to the one I explained in R3. So if I impose that the magnetic flux, the total magnetic flux is 0, then in that case, I can always find some vector field whose curl is equal to B. Or more in this intrinsic language, I have a one form that whose exterior differential is equal to B. And in that setting, the dynamics is very similar to the one in R3. I get that the motion of the particle, classical particle, is Hamiltonian again, and total energy is exactly the same as before. So instead of P, I've written C here, and alpha is simply the magnetic vector potential. Okay, so it's very similar to what happens in the planar case. If I want to quantize this equation and get the quantum counterpart, this is a little bit more complicated. So I get again a Schrödinger equation, but the operator of order 2 I get here is something that is called the magnetic Laplacian. And the way to define it is simply you do the following. You start by considering an operator of order 1 that acts on functions that does the following. So you take a function and then you map it to the differential. This is the usual differential, which coincides with the exterior differential on zero forms. And you add this one form here. So alpha is a one form, and I add this one form multiplied by the function psi. So this is the sum of two one forms. Okay. And if I consider the adjoint in L2 of this operator, and I compose this guy with its adjoint, I get what it is called the magnetic Laplacian. So when the magnetic field is zero, what I get here is minus the usual Laplacian, okay? And if I switch the magnetic field on, I get a differential operator of order 2 that is a little bit more complex. So this is because I made the assumption of the total magnetic flux being equal to zero. If the total magnetic flux is not equal to zero, then you cannot in general quantize the equation. You have to add an extra condition, which is called the direct quantization condition, which tells you that the magnetic flux must be an integer multiple of 2 pi, okay? And then things get a bit more complicated because the operator can no longer act on functions. There is some phases that bother you, and you have to make it act on the sections of a complex Hermitian Lamb bundle. So this is quite complicated, so I will keep things simple and assume this condition. This condition makes that everything looks like a PDE, a usual PDE, acting on functions. So, and the thing is that we checked what happens in this more general setting, and we don't get any new effects. So it's quite natural to keep things in that simpler setting. So the problem I'm interested in is the control problem for this magnetic Schrödinger equation. So essentially, I'm interested in knowing whether or not the magnetic Schrödinger equation is controllable from an open set on the inside of my surface. So M is a surface. Very soon, this will be the sphere, the usual sphere. But the problem, you can set it up in any surface that you like. And you take an electric potential that is real valued. And you ask the following. No? You take two states in L2. And you ask whether or not you can find a control that is in L2 in times from 0 to capital T. Such that the solution that starts at t equals 0 from the state psi0 arrives in time capital T to the state psi1, modulo acting with a control that is localized in X in the set little omega. Okay? So I have a little omega here is the set where my control acts, and I would like to control the equation by acting only on this little set. So if this happens, I will say that the magnetic Schrödinger equation is controllable in time t from the open set omega. So this is what we try to understand here, when this is possible. Is this possible for any omega? Are there conditions on omega and t for this to hold? Okay, so this problem has a long history, and maybe interesting results start with the work of Lebeau in 92. So Lebeau found sufficient condition on the open set omega and the time t for controllability to hold. It's the geometric control condition. So this geometric control condition says that an open set satisfies the geometric control condition provided that any geodesic of the surface enters within the set omega. Okay? So this is a situation when the geometric control condition is satisfied. Here omega is this region here. This is the sphere, so geodesics are simply diameters, great circles, intersection of planes that pass through the origin with the sphere. And you see in this region, every geodesic on the sphere, every great circle on the sphere passes through this region. And this one, the geometric control condition is not satisfied. So there is this red geodesic that does not intersect omega. So omega can be very big until it can be almost a hemisphere, and this will still work. And Lebow proved that if the geometric control condition is satisfied, then automatically the Schrödinger equation is controllable. Okay? This is Lebow's theorem. So there is, of course, a natural question. This is a sufficient condition? Naturally, one wants to know if this sufficient condition is necessary. Okay? And it turns out that, in general, this is not necessary. For instance, if your surface, or more generally your manifold, is a torus, and you don't have a magnetic field and not an electric field, so in that case, you can prove that the Schrödinger equation is controllable from any open set and in any time. So in this case, the geometric control condition is highly non-necessary because controllability holds regardless of the geometry. But this is in this very specific case in which the manifold is a torus. Okay, if in different geometries, this may be not true. So this is a result that Jafar and Komornik proved in the late 80s, 90s, using the theory of non-harmonic Fourier series. And well, this result was improved later on. So if you have a non-vanishing electric potential, then you have no longer control on the precise form of the eigenfunctions of minus Laplacian plus V. So you cannot use any longer this theory of non-harmonic Fourier series. And well, there are a series of works where we try to understand what happened and V is different from zero, sorry. In the case of magnetic fields, so if you are in a torus, in fact, you can take constant magnetic fields that have non-zero flux, and in that case, it's possible to show that the same result holds when you have a magnetic field. So I didn't say, but what we proved here with Nani and Taraman, and then also Bourgain, Burkowski, Bourgain, Burzou recently, is that the same thing that holds without potential holds when you add a potential. So in the magnetic field case, it's the same. And recently, Kevin Lebalc, New, and Chen-Min Sun proved that if you take a variable zero flux magnetic field on the torus, then controllability holds under a weaker condition than GCC, the geometric control condition. In their paper, they don't prove that this holds for any open set at any time, but they give a weaker condition and a geometric control condition under which this holds, okay? Other examples, interesting examples, is what happens when the curvature is negative. In that case, you get the same thing as in the torus, okay? At least when the magnetic field is zero. This is some not so old result by Dyatlov, Jin, and Annemacher. So on the other side, if you look at the sphere, then there is a very old result by Jacobson and Zeldich from 97, where they prove that in fact, in a sphere, the geometric control condition is necessary for observability of the Schrödinger equation. Necessary in the sense that if my observation set omega has the property that the complement of its closure contains a geodesic, then the Schrödinger equation is not controllable. Okay? And well, if you want to add a potential, electric potential, then the same conclusion holds. Okay, so this is I proved this some time ago, and then we improved these results with capital Rivière a little bit later. Okay, so this is a situation in the sphere when you don't have a magnetic field. Okay. And there are other examples where the geometric condition is necessary in the sense I've written here. Okay, this is not exactly the converse, but it's almost the converse. No, it's if the complementary of the closure contains a geodesic, then you are not controllable. So the same holds if you are in a Zoll manifold. So manifold is simply a manifold or a surface, if you want, such that every geodesic is closed. And the funny thing is that there are many of those, in fact, that are different from the sphere. Okay, there are surfaces of revolution with this property, and in higher dimension, there are many also Zoll manifolds. So in that case, the same conclusion that was holding in the sphere holds also in the Zoll manifold case. So you see, the thing is that the geometry of the manifold is important to understand whether or not you can control the Schrödinger equation. It's different from the wave equation. In the wave equation, you have a universal law that is independent of the geometry. It's the same condition. Okay? In the heat equation essentially is also the same. But for the Schrödinger equation, the condition depends on the geometry. In the torus, you get one condition. In the sphere, you get a different condition. So the natural question to ask here is, what happens when you are in the sphere and you add a magnetic field? Do you get also that geometric control condition is necessary in that case? Of course, if I'm giving this talk, it's because there is something interesting going on. And the thing is that in the sphere, if you add a magnetic field, then the geometric control condition is no longer necessary. And in fact, what I want to explain you in the rest of my talk is what is in fact, the necessary and sufficient condition that you get when you plug in a magnetic field. Okay, so this is the goal of my talk. So it will take me a little bit to get here because I need some geometry first. So my geometric condition, it will be a geometric condition again, will be expressed in terms of the magnetic field, but in a way that is not completely direct. I need to introduce some objects. So the main object that I need to introduce is what I call the magnetic radon transform. So the radon transform on the plane is simply the correspondence that associates a function to the function defined on the average of the function on all straight lines. Okay. On the sphere, the radon transform acting on a function is simply you take a geodesic and you average the function on the geodesic and you get a function. The radon transform is defined over the space of geodesics. So in the case of magnetic fields, you can also introduce a notion of radon transform. In the case when the flux is zero, in the case when the magnetic field comes from a vector magnetic potential. So in that case, you can do the following. The magnetic radon transform, that is again a function defined on the space of geodesics of the sphere, is defined as follows. So, well, I've defined it here on the phase space. So this is x, a point in the sphere, and xi, a tangent vector at x on the sphere. So the recipe for constructing this magnetic radon transform is the following. You consider xi. You take xi and you look at the geodesic that starts at time zero at x with velocity xi. So imagine this is the geodesic. So the next thing you do is you consider the half sphere that has the property that the vector product of position times velocity points in the direction of that hemisphere. So in this case, if I take position and do the vector product with velocity, I will get the vector that points towards the North Pole. So I take this hemisphere. And what I do is I simply integrate my 2 form B on this hemisphere. If I apply Stokes' theorem, I get that this is equal to the line integral of the magnetic field along the geodesic. Okay? This is Stokes' theorem. So this is the way you define the random transform. Okay? So it's a function defined on x and psi, x a point in the sphere, psi tangent vector to the sphere at the point x. And in fact, by definition, this is a function that is constant on geodesics. So on this geodesic, this function takes the same values all the time. Okay? And it has more interesting properties. In fact, it's homogeneous of degree 0 in psi. So if I make the modulus of psi change, the random transform won't change. And it's odd in the variable psi. So I didn't say that if I change the sign of psi, what I'm changing is simply the orientation of the geodesic. So if I change the orientation of the geodesic, the random transform changes sign. It's an odd function, okay? And the magic here is that is very peculiar to the sphere is that in fact the space of geodesics, so the random transform is constant on geodesics, so I can view it as a function defined on the space of geodesics. So the space of geodesics, in fact, can be identified to the sphere itself. So in fact, this random transform, I can imagine it as a function defined on the sphere rather than a function defined in this more complicated space of geodesics. How do I do this identification? So it's very simple. It's the same thing I explained before. So if I have a geodesic, let's imagine is this one, this equator. So this geodesic is determined by the plane where it lives. The plane where it lives is the plane that is spanned by the position of some point on the geodesic and the tangent vector of the geodesic at that point. This spans a plane, and the geodesic is precisely the intersection of the sphere with that plane. Okay? So if I look at the vector product of position times velocity, what I get is this vector here. And since everything, so I take the vector product with the normalized unit vector in the direction of psi. So this guy here is again a point on the sphere. And if my geodesic is oriented in the opposite direction, then I will get this one here below the South Pole. So in fact, this recipe identifies any point in the sphere to a geodesic, an oriented geodesic, in fact, because the one turning this way is identified to this point here, and the same geodesic oriented in the opposite direction is identified to the South Pole. So oriented geodesics are identified to points on the sphere with this recipe here. So instead of thinking of this random transform as an object that lives in this weird space of geodesics, I will understand it as a function acting on the sphere itself. So this function, in fact, defines a Hamiltonian vector field with respect to the symplectic form on the phase space, on the cotangent space of the sphere. And this flow, so this is simply a solution of some ordinary differential equation on phase space. I can view it, in fact, as a flow defined on the sphere itself because of the identification I was telling before. So in fact, I have a dynamical system defined by B, by the random transform of B, acting on the sphere to itself. Okay. So phi B is simply the Hamiltonian flow. I will give an example later on, so this is not so abstract. We'll give an explicit example of what this is in some specific situation. But just think about it as some dynamical system I create using the random transform of B, the magnetic random transform of B. And with my identification, this is a dynamical system on the sphere. I can think it as a dynamical system that maps geodesics into geodesics or points of the sphere into points of the sphere, either way. Okay. So what is the magnetic geometric control condition? So we start by considering the set consisting of all geodesics that are not controllable. That is, the geodesics that do not intersect the control set. Okay, so these are if this set is non-empty, it means that the geometric control condition doesn't hold. Okay? That the geometric control condition holds means that this set is empty. So this in principle will be non-empty, and I will define the magnetic control time. The magnetic control time is simply the time it takes for every geodesic that is not controlled to reach some set A by means of this dynamical system acting on geodesic that is constructed using the magnetic random transform of the vector potential of the magnetic field, sorry. Okay? So I take the minimal time it takes for every geodesic that is not controlled to get in here. So the theorem says the following. So if I consider the time with, instead of A, I put the closure of omega. If I take a time that is smaller than this one, then the magnetic Schrödinger equation is never controllable in time t from the set omega. Okay? And conversely, if my time is bigger than the time defined by this recipe, putting here omega, so this time simply the time that it takes for every geodesic that is not controlled a priori to get into omega by means of this dynamical system acting on geodesics phi b. Okay, so this is a completely different situation. As you can see, there is a minimal control time, which did not happen in any of my previous examples. In my previous examples, I didn't emphasize it, but all examples hold regardless of how big or small the time was. And in this case of magnetic fields in the sphere, we get that the geometric control condition that is necessary and sufficient involves a minimal controllability time. Okay? So let me comment a little bit on this condition. And well, first disclaimer. So generically, the two times, the necessary condition and the sufficient condition are the same, but there are situations where they are not the same. Okay, and the quality here is strict. Simple cases. You take omega to be a hemisphere, and so if you take the time when with no magnetic field associated to a closed hemisphere, you get 0. This is automatically because the control condition holds for any time t. And if I take the omega open here, then the time is infinity because in this situation, geometric control condition does not hold. So there are very simple situations in which the two times are different. So one has to be careful. So there is some gap there, okay? So in which cases the geometric control condition doesn't say too much. So case where it doesn't say too much is the case where you get a critical point of the magnetic random transform. So this magnetic random transform, this is essentially a function defined on the sphere. So it has always critical points. Okay, it has always critical points because a function on the sphere has at least a maximum and a minimum. So there are two critical points. So when I view it as a function defined on the space of geodesics, since my radial transform is an odd function, this amounts that there is at least one critical point that corresponds to the same geodesic that is in the two possible orientations, okay? So if I have a geodesic that is a critical point, then this geodesic is stationary by this vector field. In particular, if it was not in k omega at the initial time, it will never be there because it is stationary. So necessary condition that you get is that if your observation set, the complementary of the control set contains a geodesic that is a critical point of the random transform, then the magnetic Schrödinger equation is never controllable from omega for any time t. So you get a strong necessary condition here. In particular, there is a case where our result is empty. Well, it's not empty, but there is nothing new happening. It's the case in which the magnetic field is an odd function, is an even function, sorry. In fact, one can prove that the random transform is an isomorphism from odd functions on the sphere to odd functions on the sphere. And its kernel, when you read it as a function, an operator acting on C infinity function, is exactly the space of even functions. Okay. So if you have an even magnetic field, then in this case, the geometric control condition is again necessary. Okay? If your magnetic field is even, our result shows in particular that geometric control condition, the Lebow condition, is necessary in this case. So when it is different, so it's different, of course, when the magnetic field is odd. your magnetic field or it has another component. So this is the simplest magnetic field you can think of. So I said that this was a, I said this, there is maybe a question or, oh,
Oh, I think it's someone was saying hello.
hello. So I was saying that this is an isomorphism, no, from odd functions to odd functions. So in particular, if I take x3, this is a very nice odd function on the sphere, no? It's the height function. And this is odd by definition, it's a polynomial. So I can consider the magnetic field that corresponds by my identification, the magnetic field whose radon transform is x3, okay? This is a well-defined magnetic field, okay? That has flux zero, etc. So in that case, you can compute explicitly everything. And this flow that is quite mysterious, in fact, in this case, is very simple. It's simply the rotations fixing the axis x3. So it's simply you're rotating like this. Okay. So in this case, you get a very nice explicit geometric control condition. In fact, our result for this potential tells that if you have, for instance, if omega, the control set, is any neighborhood of one point in the equator, x3 equal to 0, for instance, 1, 0, 0, can be very small, this neighborhood, as small as you want. Then the magnetic Schrödinger equation is controllable from omega as soon as the time t is greater or equal than p. Okay, this is a concrete realization of our theorem. Okay, so omega can be very small. Omega is this guy here, can be super tiny. Okay, of course, if it's very small, it does not satisfy the geometric control condition because there are many geodesics that are not entering here. So our result says that if you wait at least time pi, sorry, then the equation is controllable. And why is this? Simply because the flow phi b, which is rotations, so you see the geodesic here corresponds to the North Pole. And this neighborhood of points in omega, if I look at the geodesics issued from points in that neighborhood, is essentially that something that has this shape. So when I make my identification of points with geodesics, so the geodesics that starts from omega are essentially represented with my identification as something like this, some neighborhood of this guy here. Okay, so what happens here is simply that any other geodesic, which is any other point here that is not in this omega, when I apply my flow phi b, this will be a rotation following in that direction, following clockwise direction in the anti-clockwise direction with respect to the axis x3. So every geodesic which is represented as a point like here, at some point will enter here. Okay, this is what we get. Okay? So you see, situation is quite different. And of course, if you take any spherical harmonic, you can do this computation and you will get essentially an explicit flow and you will get a different condition. Okay, you will get a geometric condition. You can really compute these things. So how do you prove this? Since I should finish in 2 minutes, I want to talk to you with the proof. If you're interested in the questions, I can answer. I will give you a little bit the structure of the proof. So the first steps are very standard. The first thing is to formulate the problem as an observability problem. And then you try to, so the necessary and sufficient condition, you can address it by contradiction. Now you can suppose that you can simply try to investigate when observability is violated by some sequence of functions. Okay, so this is the point of view that we take. And we analyze sequences of solutions that violate observability using Wigner distributions and semi-classical measures. And we get transport equations for Wigner distributions. First order, this equation will give you that geometric control condition is sufficient. This is Lobos result. And the point is to try to get more information from the transport equation for Wigner distributions. And this is the key thing we do. So we get extra information from this equation for Wigner distribution using a technique called the Weinstein averaging method that Alan Weinstein introduced in the 20s, in the 70s, sorry, his work on spectral theory. And what we get here is this transport equation that involves this magnetic flow. And combining invariance and this transport, this is exactly what we obtain when we state our magnetic geometric control condition. So I think I will stop here. I thank you for being there. And if you have any question, I will be delighted to answer.
Okay, thank you very much, Fabricio, for this very nice, also technical talk. It's passionate subject. So let's ask the audience if there are any questions or comments. As usual, you can use chat or microphone that they are open for your questions. So please go ahead. So you have applauses.
Thank you.
So one comment only, Fabricio. Thank you very much
Yes.
for your amazing talk. I was, or at least it has stand out to me the fact that it's very important the geodesic condition, no, or hypothesis for some results, no.
Which one, Yanni,
No,
sorry?
in general, I have seen that there was some properties of the geodesics that gave the possibility to obtain the control result, no? Maybe I
Yeah.
was thinking, no, I have no idea, because maybe the characteristics are something intrinsic or something very characteristic of spheres, no?
Yes. So the fact that we are in a sphere is used in this step, in the penultimate step of the proof. So I've been very quick here, but the fact that you can get extra information comes from the fact that so the thing that make work this mechanism here is uses strongly that the geodesic flow, the geodesics are periodic. All geodesics are periodic. And also that the quantum, if you look at the wave equation, the group generated by the wave equation on the sphere, this is essentially periodic too. So these two features are very specific to the sphere. And these are the ones that make work, this proof. If we are in a manifold whose geodesics are closed, you can do with a little bit more work, you can make this work too. But here we use very strongly that all geodesics are closed. If all geodesics are not closed, in general, you cannot do the penultimate step. Yes.
Thank you. Yes, it was interesting. Thank you very much.
Are there other questions? I wonder, Fabricio, if do you think there are some relation between the time and the dependence on the time and the geometry? So
Yes,
you
yes.
were, but do you have any idea which could be the dependence? I don't know, because in the examples you presented before, it was controllable for any time, but here in this case, we need to wait a little bit. So what do you think? What are your feeling?
So for when you look at the Schrödinger equation without magnetic field, there is no control time. So usually you don't there is no control time. The equation is going to be controllable regardless of how big or small the time is. The constant, of course, the cost of control will depend on that, but not the fact that the equation is controllable or not. And here the thing is that in the case of magnetic field in the sphere, this is quite surprising. You get probably this is one of the few instances where this happens. In the torus, the conjecture is that even if you have a magnetic field, you will get control for any time. You won't get
Okay.
this thing of minimal time.
Okay.
I think this is really specific of the fact that we are in the sphere. Sometimes you get this kind of thing in Riemannian hypoelliptic operators. There are many people that have work on that, and you get a similar phenomenon in hypoelliptic operators. Here, the nice thing is that we get it for a very quantum mechanical model that is quite natural, I mean, quite physical.
Mhm. Okay, thank you very much. Are there other questions or comments? So if not, we thank you again
Thanks a lot.
for this talk and for being with us in this seminar. Thank you very much.
Thanks a lot, Anna. Thanks.